All right, let's dive right into this explainer. Today, we're doing something honestly pretty exciting. We're stepping directly into the shoes of Professor Nirmal on the very first day of what promises to be an absolute masterclass in civil engineering. We're going to map out the entire journey of studying fluid mechanics and fluid machines. Now, Professor Nirmal's whole approach is all about crystal clear explanations. It's about finding the actual physical meaning behind all that complex math. So whether you're an engineering student grinding through the coursework or just a curious learner who loves figuring out how our physical world actually operates, you are in the perfect place. Let's get right to it. Before we even think about cracking open a textbook or jotting down a single equation, Professor Nirmal drops this fantastic, almost philosophical hook on his class. He asks, what's the one thing that covers nearly 71% of the Earth's surface, flows through every living being, shapes our cities, drives our turbines, and yet literally slips right through our fingers? The answer, you guessed it, is water. But as this class quickly reveals, we aren't just talking about water here. We're talking about air, oil, steam, the countless fluids that are constantly pushing, lifting, and powering our modern world. This subject isn't just a bunch of abstract formulas on a chalkboard. It's about deeply, truly understanding the behavior of these fluids so we can actually harness them. So, part one, why fluid mechanics matters and the stakes of civil engineering. What's truly fascinating about this is how it fundamentally redefines what a civil engineer actually does. I mean, we usually just picture roads and buildings, right? But engineers build our absolute lifelines. We're talking water supply systems, towering dams, winding canals, massive drainage networks, sewage treatment plants, and those vital fire protection systems. And here's the kicker. Every single one of these massive infrastructure projects relies entirely on understanding fluids under pressure or fluids in motion. Without mastering fluid mechanics, designing systems that are safe, efficient, and sustainable is basically impossible. Which brings us to a crucial point. In this field, failure is simply not an option. Just imagine designing a massive city pipeline that suddenly bursts under immense pressure. Or think about a critical pumps failing right in the middle of a catastrophic flood. What about a hydroelectric turbine that just doesn't generate the expected power? The consequences of a poor design here aren't just a bad grade on a final exam. They can be disastrous. They cost millions, and they can even be life-threatening. This harsh reality is exactly what anchors the absolute necessity of mastering fluid behavior. We aren't just learning to pass a class. We are literally learning to protect and power civilization. Moving on to part two, motion and pipe flow. We're going from microproperties to macro networks. We have to begin at the foundation. What exactly is a fluid, and how on earth does it differ from a solid? Well, this is where we define the fundamental properties, things like density, viscosity, surface tension, and compressibility. From there, we step up to the absolute laws governing fluid motion. You've got the continuity equation, the momentum equation, and of course, the legendary Bernoulli's equation. Think of these as basically Newton's laws, but for fluids. And Professor Nirmal grounds these concepts so perfectly. Like, have you ever had a doctor measure your blood pressure? That is actually Bernoulli's principle in action, right inside your own body. We also explore how engineers use clever devices like the Venturi meter, orifice meter, and pitot tube to measure flow in pipes based on these exact same laws. Now, when we scale those micro properties all the way up into macro networks, we have to dive a lot deeper into how fluids actually flow through pipes, ducts, and channels. We study laminar versus turbulent flow and boundary layers, but honestly, the real star of the show here is friction loss. Have you ever wondered why water pipes in major cities vary so wildly in diameter? Or why municipal pumps have to be placed at very specific, strategic locations? It is all because of friction loss and flow analysis. Engineers rely on complex mathematical models, like the Darcy-Weisbach equation, and highly practical visual tools, like the Moody diagram, to design these incredibly massive, efficient pipeline systems. Next up is part three, models, pumps, and turbines. It's all about predicting and powering the future. This part begs a massive question. How do we actually know a colossal structure is going to hold up against the sheer forces of nature before we spend millions of dollars to build it? Well, the answer lies in the brilliant science of scaling, known as dimensional analysis and similitude. This is literally how we predict the future. We don't just guess how a massive new bridge or a towering dam will react to a catastrophic flood. No way. We use similarity laws to test small-scale models in laboratory water flumes first. It allows engineers to accurately predict the behavior of real, full-scale systems without having to build them. It's an incredibly powerful concept that saves immense amounts of time, money, and valuable resources, all while ensuring public safety. And you've got to appreciate the beautiful, almost poetic symmetry of fluid machines here. On one side, we have pumps. Pumps are devices that add energy to fluids. They do the heavy lifting, pulling water from deep underground wells, pushing it way up to high-rise buildings, and supplying our home overhead water tanks. Engineers carefully study their efficiency, cavitation, and how they operate in series or parallel configurations. But then, on the exact opposite end of the spectrum, we have turbines. Turbines extract energy from flowing water and convert it into mechanical or electrical energy. Whether we're talking about Pelton, Francis, or Capelin turbines, these are the beating hearts of hydropower. They drive massive projects like the Bakranangal and Tahiri dams. So one machine gives energy to the water, the other takes it right back to power our grid. It's an amazing cycle. Finally, part 4, how to master it, opening up the professor's toolkit. We've covered the what and the why, so let's shift over to the how. How do we actually learn this incredibly complex material? Well, Professor Nirmal breaks down the ultimate logical sequence. Step 1, concept first. You always begin with why something happens in nature. Step 2, formula next. Once you grasp the why, then you figure out how to calculate it. And step 3, real-world application. You solve problems taken directly from actual field situations. He constantly stresses that mastering this subject heavily relies on visual learning, animations, lab demonstrations, actually seeing the fluid behave with your own eyes. It is absolutely not about rote memorization. It's about deeply understanding and then applying those physical principles. I absolutely love this piece of advice from the professor. He says, don't be afraid of the equations. They are just compact ways of describing nature's behavior. For anyone who gets totally intimidated by complex algebra, calculus, or physics, this is just such a comforting, profound way to look at it. Mathematics is really just a tool. Once you understand the physical meaning, once you get the actual story that the equation is trying to tell you, that intimidating equation simply becomes your friend. To wrap up this explainer, Professor Nirmal leaves us with these fantastic, thought-provoking everyday mysteries. Think about it. When you look at a rain puddle, or a flowing tap, or feel a strong breeze, why does water take a certain shape? Why does air move faster around some objects? How does a simple medical syringe actually draw liquid upwards? And how on earth does a massively heavy steel ship float on the ocean? The answers to all these questions lie directly in the science of fluid mechanics. Learning this completely changes the way you see the physical world. So, the next time you turn on a tap or feel the wind against your face, ask yourself, are you just experiencing nature, or are you finally seeing the master equations that govern our universe?